Hello, it is I, Arune, and today we're going to talk about centripetal acceleration. So, in order to grasp this concept, I want to first introduce you to my friend, the circle. The circle has 2 points on it, velocity 1 and velocity 2, or VI or VF, whatever you want to call it. Now, it should be noted that on this diagram, the velocities are constant. VI is the same as VF. You know, you'd usually say, if this was in a straight line, you'd say that there's zero acceleration, since it isn't slowing down, it isn't slowing up, and it isn't turning. But in a circle, you can see that there is clearly turning. So that is the concept we're trying to tackle today, centripetal acceleration. Now, in order to get the equation for centripetal acceleration, we have to go through a couple of steps. The first is we need to understand the geometry of a circle. So there's the equation for arc length that we have. And the equation for arc length is S equals theta multiplied by R. Now, in this scenario, we can see that we have different constants. So, for instance, in this circle, the S would be the velocity multiplied by the change of time, since it's going on a change of time from one point to the other point and the velocity is constant. Now, it should be noted that the final velocity is equal to the initial velocity plus the change of velocity, due to the fact that the change of velocity is equal to the velocity final minus velocity initial. It's just a rearranged equation. And also, we created a little triangle, another similar triangle, similar to this one, to illustrate the velocities at different points. So this is VI, this is VF, and that's the change in velocity. In fact, it's this concept that allows us to get 2 different angles. So the first angle we have is S over R. The second angle we have is the change in velocity over the velocity. And now we have to acknowledge that since these are similar, these are equal to each other as well. So if you substitute the V times change in time for S, and then you rearrange it so that we have V, the change in velocity over change in time, we get that the change in velocity over change in time is equal to V squared over R. And since the centripetal acceleration is equal to change in V over change in T, generally speaking, we apply it to the point where it becomes V squared over R. And that is how we get the derivation of centripetal acceleration.
Okay.
Hey, this is another sample question for our unit that we're covering. And here it is. A road has a curve baked at a velocity of 12 meters per second with a radius of 150 meters. Draw a free body diagram of the situation and find the angle. So say you're on I-95 and you're turning on one of the bumps. That's practically what this question is. So pretend this box is our little car and the line is our surface. So we have the force, the normal force the surface exerts on the car going up in that direction, which I split up into its components. I'll explain why I did that later, and I'll explain why I did that for the force of normal later. And then we also have the force of gravity that's always downwards. So the real reason why I split up the force of normal into those 2 components is because they both go in different directions. One of them goes into the radial direction, and the other one goes into the y direction. So, to start off with this problem, we should probably go towards the radial direction. So we have the net force of the radius is equal to MAR, which is the radial acceleration. Then we substitute the radial acceleration for V squared over R. And then, as we can see from our from our free body diagram, since Fn sine theta is in the radial direction, the direction at which the highway curves, it's going to be it's going to be F net R, essentially. So we'll leave that alone for now. Now let's focus on the Y component. So for the Y component, we have Fn cosine theta going upwards and Fn sine theta going downwards. And since there's no acceleration in the Y direction, this section essentially becomes 0. Since we want to know what the normal force is in this equation, we algebraically solve this component to the point where we get the normal force. After we get the normal force, it's just a matter of plugging and chugging. But to be more specific, I guess I should say that we substitute mg cosine of theta into the f of n space in there. And then afterwards, we realize two things. The first thing we realize is that sine theta over cosine theta is tangent of theta. And the second thing we realize is that there are two m's on there, so they cancel out. Now it's just, since we want to know what the angle is, it's just algebraically solving to get the angle. And after plugging and chugging the variables at the top, we get that the angle is 5.59 degrees. Yeah? Okay guys, so this is going to be a late video, but it's alright. So this video is going to be about universal gravitation and the laws and the equations for it. So the first equation we have at the top is the force of gravity is equal to big G, big M times small m all over r squared, with big G being 6.67 times 10 to the 11th Newton meter squared over kilogram squared. So what this equation is essentially saying is that if you have two masses and they're like a set length r apart, they will feel the force of gravity as such. So what this means is, or what the r squared on the bottom practically means that the closer they are, the more force they will feel, whereas the farther they are, the less force they will feel. And since this is, we can see here that it is inversely proportional, or inversely squared. So that means that the farther it is, the more or less feeling of gravity it would feel, essentially. And now this is the other thing. This is the Cavendish experiment. The Cavendish experiment is what was used to find out the gravitational constant. And what they did is they had a wire, and the wire was connected to a pole with two masses. And the two masses were attracted to two other masses, and they calculated the torsion to find out that the big G constant, essentially. Okay, so now that we got that equation out of the way, which you could use to do many things like, I don't know, solve the force of gravity from two planets, or solve the acceleration of due to gravity on a certain planet. So now that we found that, the next thing we need to talk about is the potential energy, or potential energy due to gravity. So we know the general fact that work is equal to the integral of force over distance. So if we change that to the force of gravity over the distance dr, and we integrate with respect to r, we get that the potential energy due to gravity is negative big G m small m r. And yeah, that's all I'm gonna say. Yeah. Goodbye. How do I stop this?
Go. So, our problem is find the magnitude and direction of the net gravitational force that bulb B feels in the diagram below. So this is a diagram. So ball A is 2 kilograms, ball B is 5 kilograms, ball C is 2 kilograms, and they're all half a meter away from ball B. So what I first did is I defined an X and Y axis, and then I used the force, like the gravitational force, which the the equation for it is the gravitational constant times the mass of ball A versus ball B over the radius or the distance, which is half a meter. So you plug that in, which is ball A and ball B, and then you get 2.67 times 10 to the negative 9 newtons. And the force from ball C to ball B is basically the same since they're the same mass. And after that, you can solve the direction of this using a free body diagram, in which, not really, but like you can solve for the net force by making this diagram so FA on B would be in the x direction and FC on B would be in the y direction. And then you basically solve for this angle right here by using the inverse tangent, which is the opposite over the adjacent. So it's FC on B, which is 2.67 times 10 to the negative 9 newtons, over FA on B, which is the same. So you get 45 degrees. So it's 45 degrees below the x-axis. So then you solve for the F net using the Pythagorean theorem, and then you get 3.77 times 10 to the negative 9 newtons, 45 degrees below the x-axis.
Okay, so one of the questions you may be asked is, what is Earth's escape velocity? Or you might be asked the escape velocity of any planet. This is a way to derive that equation. So first we start with this equation because this involves kinetic energy. So the work done is equal to the change in kinetic energy plus the change in potential energy. And we can very easily take this to the next step. There is no work done, so the work done is equal to 0. And the change in kinetic energy and the change in potential energy can be changed into the kinetic energy final and the minus the kinetic energy initial, and the same thing for potential energy. So now that we've got that, we can insert our equations. So the equation for kinetic energy is always 1/2 mv squared. However, the equation for potential energy, for gravitational potential energy, is negative g times the mass of the object times the mass of the smaller object over the radius. And so I inserted that equation for potential energy into these spaces since we are doing the gravitational potential energy. And then we can cross out 2 of these equations. We can cross out this because we don't care what the velocity is after it escapes the Earth. So it can just be 0. And since the velocity is 0, this whole part is 0. And then we can cross out this because the radius afterwards is infinite since it's away from the Earth. And since this radius is infinite, this whole thing approaches to 0. So then we just have this simple equation: 0 is equal to negative 1/2 mv initial squared plus g times the mass of the Earth times the mass of the spaceship over the initial radius, which will end up being the radius of the Earth. So then we keep going. We can take this equation for kinetic energy and put it on the other side, and so we get a simpler equation. And then it's just algebra from here on out. We just multiply the 2, we cancel out the little masses. We put the 2 to the other side, and we end up getting the escape velocity is equal to the square root of 2 times g mass of the Earth over the radius of the Earth. And now all that's left to do is plug it in. So I have the mass of the Earth, the radius of the Earth, and g, which is the gravitational constant. And then we simply plug it in, and the escape velocity is equal to 11,181. It's
What's the unit?
meters per second.
That's like Mach 32.